Floyd's algorithm. In this Floyd's algorithm, given a weighted graph, you can find shortest paths between every pair of vertices. Idea here is you are required to construct solution through series of matrices D0, D1, etc. Dn. D0 initially for the graph, whatever cost matrix you are going to write, that itself is D0, and D1 when you introduce first vertex as the intermediate vertex, you are going to achieve some path length that is indicated in D1, and D2 when you introduce 1 and 2 as the intermediate vertices, then you are going to achieve some path length, so that is indicated in D2. Finally, when you introduce all n vertices as intermediate vertices, so whatever shortest path you are going to achieve, that is indicated in Dn. We'll see with the example here. First, let us see how to write cost adjacency matrix for this given graph. So from 1 to 1, it is equal to 0, 2 to 2, 0, 3 to 3, 4 to 4. So all principal diagonal elements will be equal to 0. And here from 1 to 3, there is an edge. If there is an edge from vertex I to vertex j, then you have to write the weight assigned to that edge. If there is no edge from I to j, then for that you have to write it as infinity. We'll see how to write for this graph. 1 to 1, 0. 1 to 2, there is no edge, so write it as infinity. 1 to 3 is 4. 1 to 4 is infinity. Then from 2 to 1, it's equal to 1. 2 to 2 is 0. And 2 to 3 is 6. 2 to 4 is 3. Similarly, from 3, there is no outgoing edge. So write it as infinity, infinity. 3 to 3 is 0. Then 3 to 4 is infinity. Then from 4, it's going to only 3 and 2. 4 to 1, there is no edge, write it as infinity. Then 4 to 2, it is 5. 4 to 3, it is 1. Then 4 to 4, 0. So this is how you can write cost matrix. Next, we'll see how we can change the path length or how to find the shortest path between the given pair of vertices. Now look at the diagram here. There is no direct edge from Vi to Vj, but you can reach to Vj via Vk, because there is a path from Vi to Vj, but there is no direct edge from Vi to Vj. So initially, Vi to Vj, it is equal to infinity. That is, in the previous iteration, it is equal to infinity. Now you are introducing kth vertex as the intermediate. So when you introduce kth vertex as the intermediate, then from Vi to Vj, the path length will be equal to 20. How? We'll see how this can be done. In order to change the value, because kth vertex you are introducing as the intermediate, for that you just box kth row and kth column. Now there is no direct edge from I to j, okay, or there may be a edge from I to j, but path and edge weight may be more here. We will see whether to replace or not this value. For that you have to take a decision. So in that case, consider this value, that is dij, comma, dik is 10 and dkj is this. So these two values is to be added. When you add, it is equal to 20. Now compared to infinity, 20 is the minimum. Replace dij with value 20. This is how you are going to do. For example, if you want to introduce the first vertex as the intermediate vertex, then you are required to box first column and first row. So we will see with the example. In Floyd's algorithm, you have given with weighted cost matrix. So here you are required to change the path length between every pair of the vertices. So for that you are required to vary I from 1 to n, vary from j from 1 to n. This is for every pair of vertices. You are required to do the changes. And how many such iterations you are required to do? N iterations, because there are n vertices in the graph. Obviously, to introduce first vertex as the intermediate, one iteration, then second vertex as intermediate vertex, then again you have to do some iteration. So like that, you are required to introduce 1 to n as the intermediate vertices. So for that reason, you are required to vary k from 1 to n. So 1 to n introduced as the intermediate vertices between every pair of vertices of the graph. So once you have written this loop, then dij equal to minimum of dij comma dik plus dkj. The time required to find the solution is, it is in theta of n cube, that is it is cubic. And every time if you are overwriting the same matrix, then space requirement here is n square. And this is working on negative edges also, but it should not contain negative cycles. So with that you can find the shortest paths between every pair of vertices. We'll see how to apply this Floyd algorithm for this graph. Look at here. 1 to 1, write it as 0. 1 to 2, there is no direct edge, write it as infinity. 1 to 3 is 3. 1 to 4 is infinity. Then from 2 to 1 is 2. 0. From 2, there is no edge from 2 to 3, so write it as infinity. And 2 to 4 also there is no edge, it's write it as infinity. Then from 3 to 1 there is no edge, infinity. 7, because 3 to 2 is 7, 0, then 3 to 4 is 1. Then from 4 there is only one outgoing edge, that is it's going to 1, so write it as 6. Remaining 2 write it as infinity. 4 to 4 equal to 0. So look at here, 1, 2, 3, 4, 5 edges. So there are 5 edges, and in the cost matrix 1, 2, 3, 4, 5, we have 5 values. Remaining either it will be equal to infinity or it will be equal to 0. So once you have done that, now we'll see in the first iteration, first vertex is introduced as the intermediate vertex. So introduce first vertex as the intermediate. For that, you are required to box the first row and first column. In the first row, the column element boxed is 0. You cannot expect any change. In the second row, you may expect some change. We will see. Now 2, 2 plus 0. So it remains same. 0, 2 plus infinity. It's infinity. So 0 itself is minimum. Then infinity, 2 plus 3. 2 plus 3 is 5. So compared to infinity, 5 is smaller. So replace infinity with 5. Infinity, and then 2 plus infinity is infinity itself. So no change here. Then in this third row, the column element boxed is infinity. No need to cross check whether it is going to minimize the path length or not, because for any value, if you add infinity, you will get the value infinity itself. So write the third row as it is. In the fourth row, 6 plus 0 is 6 itself, and infinity, 6 plus infinity. So infinity itself. Here infinity, 6 plus 3 is 9. So replace this infinity with 9. Wherever 0 is there, you need not have to cross check, because 0 itself is the minimum value here. We are not using any negative weights. So better you write it as 0 itself, no need to cross check here. So with this, if you introduce first vertex as the intermediate, the path length we are achieving like this. Look at here. In the diagram itself, you can able to make out between 2 to 3. There was no 2 to 3, there is no direct edge. But when you have introduced the first vertex as the intermediate vertex, you can get the path length equal to 5. Look at here, 2 to 3, there is no edge. But after introducing the first vertex as the intermediate, you can get the path length equal to 5. How? 2 to 1, 1 to 3, right? Similarly, one more change we have got here. What is that? 4 to 3. 4 to 3, there is no direct edge. But after introducing 1 as the intermediate, so you are getting the path length equal to 9. So this is how you can find the shortest path between every pair of vertices. Now in the second iteration, you are introducing second vertex as the intermediate. So box the second column and second row. In the first row, the column element boxed is infinity. So you cannot expect any change. Even in the second row, here the column element boxed is 0. No need to cross check, because for any value, if you add 0, you'll get back the same value. So no need to cross check here. We'll see in the third row. Third row, the column element is 7. 7 plus 2 is 9. So infinity comma 9. Minimum is 9. So replace this infinity with 9. Then 0 write as it is. Then here 1 you have, and 7 plus infinity is infinity. So 1 comma infinity, 1 itself is minimum, write it as it is. Then here you have 6. We'll see whether to replace 6 with some value or not. 6 comma infinity plus 2 is infinity. So 6 itself is minimum. Here write infinity as it is. Then here 9. We'll see whether to replace 9 with some value or not. 9 comma infinity plus 5. That is infinity itself. So 9 you retain as it is. Here 0, because this is the least possible value, write as it is. So in the third iteration, you are introducing third vertex as the intermediate. So box third column and third row. So write 0 as it is. Then the column element boxed in the first row is 3. 3 plus 7 is 10. Infinity comma 10. 10 itself is minimum. Write 3, and then infinity 3 plus 1 4. Minimum is 4 itself. Next, 5 plus 9 14. Earlier it is 2. So don't replace this 2 with 14. Here 0 itself is the minimum, and 5, and here infinity comma 5 plus 1, it's equal to 6. So compared to infinity, 6 is minimum. Replace infinity with 6. In the third row, the column element boxed is 0. Write this row as it is. In the final row, it is 6 comma 9 plus 9, 18. 6 is minimum. Then infinity comma 7 plus 9, 16. So 16 is minimum. Write it as 16. Then write 9, 0 as it is. Then finally, we are introducing fourth vertex as the intermediate vertex. We'll see what changes is going to happen. In the first row, 0 write it as it is. Then 4 plus 16, 20. 10 is compared with 20. 10 itself is minimum. Write it as it is. 3 comma 9 plus 4, that is 13. 3 itself is minimum. Write 4 as it is. Then 6 plus 6, 12. 2 is minimum. Write 2 itself as it is. Then 0, no need to replace. Then 5, 15. 5 itself is minimum. So you have to retain that as it is. So 6 comma 6 plus 0, 6 itself. So here you have 9 here. Then 1 plus 6. 1 plus 6 is 7. So Here 9 is compared with 1 plus 6, 7. So 9 comma 7, 7 is minimum. Then 7 comma 16 plus 1, 17, 7 itself is minimum. 0 write as it is. Then 1 comma 1 plus 0. So 1 itself is the answer here. In the final row, you need not have to cross check because the column element boxed in the final row is 0. Anything added to 0 will be same value you are going to get. So no need to cross check the final row. So with this, you can cross check between every pair of vertices, whatever it's there in the cost matrix, that is T4. This itself is the minimum path length. So look at here, from 1 to 2. 1 to 2 there is no direct edge, but still you can get the path length equal to 10. How we could able to achieve this path length? 10 via 3. That is 1 to 3, 3 to 2. The path length is 10. So that too we got it in the third iteration. In the second iteration, look at here, we have not got anything here. So after introducing the third vertex as the intermediate, we are getting this path length equal to 10, right? Similarly, so when you have introduced the third vertex as the intermediate, so you can able to minimize the path length from 3 to 1. Earlier it was 9. How you got 9? From 3 to 1? 3 to 1. 3 to 1. So here 3 to 2 is 7. 7 plus 2 is 9. So when you have introduced second vertex as the intermediate, in the second, after the completion of second iteration, we got 3 to 1 as the value 9. But after introducing third vertex as the intermediate vertex, we are achieving the path length equal to 7. How? So 3 to 1. So how did you get that 7 here? 3 to 2, 2 to 1 is 7, 1 to 3, 1 to 3 is 3. So you're finally, in order to achieve this, you have to introduce fourth vertex as the intermediate. Then only you can achieve this path length equal to 7. So 3 to 4 is 3 to 4 is 1, 4 to 1 is 6. So the finally what we are getting is this.